how exactly electric field affects the other charges, and how do we get to know that there is a presence of a charge, and what is the reason for it? The presence of a field there. Two lines never cross each other. It just move from one place to another place without even intersecting each other. We have to sum up because it's the influence happening at point P due to plus Q and due to minus Q both also. So E1 also is there, E2 also is there at the same point, that is P. Hello everyone, I'm Brinda, Faculty of Physics from Vidhyaashram School of Excellence, Mysuru, welcoming you all to Chapter 1, Electric Charges and Fields, and Session 2. So in today's class, we are going to deal with few of the concepts much more than that of whatever we had studied in the previous session, that is electric charges. So here we study about electric field. What is an electric field? The field is nothing but the one which gives you the presence of the charges over there. You can't see a charge, but you can feel its presence, and that presence is given by electric field. Consider a charge Q. Why a capital charge Q? Because it's called as a source charge, which is a main charge. At origin O in a vacuum condition, so Q, that is a small letter q, which is called as a test charge, which tests the charge of the source charge. So we have to consider Q as well as a Q at two different points. So on joining it, C, we get placed at P. So this is at origin O and this is placed at P at a distance R from O. Okay, this is the distance R from O. So charge Q exerts force on another charge, that is a test charge Q, as per Coulomb's law. Okay, so now the space or the region surrounding a UPC. UPC means unit positive charge. So this holds as UPC. The space or the region which surrounds this unit positive charge, it experiences electric field or electrostatic force due to the field. It is called as electric field or its intensity. Okay, so next we are coming to electric field. Electric field, how is it defined? The force experienced by a unit positive charge. So force per unit positive charge is called as electric field. With the help of this definition, we have got this equation, E is equal to F by Q. Or with the help of this equation, we can get that definition as electric field is nothing but force per unit charge. And it is a vector quantity. A vector quantity is a quantity which has direction as well as magnitude. So SI unit of this equation is nothing but force is given by Newton and charge is nothing but Coulomb. Newton by Coulomb or Newton Coulomb inverse. The other way of giving the SI unit is mole per meter. Next is dimensional formula for it. According to this holds good like MLT minus 3A inverse. Okay, and which has to have a square bracket enclosed within it. So this is all about your electric field concept. So you got to know how exactly electric field affects the other charges, and how do we get to know that there is a presence of a charge, and what is the reason for it? The presence of a field there. Okay, in the neighboring, it gives you the presence of a field in the surrounding neighbor. Okay, so field is defined as force per unit charge. You have its SI unit, you have its dimensional formula. Next, let's see electric field due to a point charge. So suppose this is a point charge, how exactly it goes? The force exerted on a positive charge Q placed at a point P at a distance R, that is, the force is experienced by this charge. This charge is called as a test charge and it experiences a force by this charge, and this is known as, that is, capital letter Q is known as source charge. Okay, electric field at a point P due to Q at a distance R, we will have E is the electric field vector quantity, which is equal to 1 by 4 pi epsilon naught. Electric field at a point P due to Q at a point P means this is experiencing, so Q by R square, distance is R. Okay, so that holds good for electric field due to a point charge. Now, source charge means what? The charge which produces electric field is called as source charge. And what is test charge? Which experiences the produced electric field is called as test charge. Charge which will test the effect of the source charge is called as a test charge. Okay. So if the source charge is positive, the electric field, how is it? It is radially outwards. Radially means perpendicular. And we have a point charge over here. If the source charge is positive, if it is plus Q, what happens? We have a radial directions, perpendicular directions to this point. It is outwards. Okay. If the source charge is negative, the electric field is directed inwards. So we have inward direction of a point charge, negative Q, it is inwards. The direction of field is inwards, which is given by this symbol. Electric field due to system of charges. Suppose we have charges like Q1, Q2 goes up till Qn. Electric field due to these charges is given by, this is given by E1 is equal to 1 by 4 pi epsilon naught Q1 divided by R1 square. And electric field due to Q2 is given by E2 is equal to 1 by 4 pi epsilon naught Q2 by R2 square. And by Qn it goes up till En, that is nth electric field due to nth charge. En is equal to 1 by 4 pi epsilon naught Qn divided by Rn square. So electric field due to system of the charges, we have to add everything. We have to sum it up. So capital letter E, summation it gives is equal to E1 plus E2. Continuity, you just 3 dots which shows continuity and En. All these are the vector quantities. So how do you write this as? This is all vector quantity, vector quantities. So 1 by 4 pi epsilon naught Q1 by R1 square plus 1 by 4 pi epsilon naught Q2 by R2 square. It goes up till 1 by 4 pi epsilon naught Qn by Rn square. Correct? You can even write it as vector E is equal to 1 by 4 pi epsilon naught of Q1 by R1 square, Q2 by R2 square goes up till Qn by Rn square. Or you can just give it in case of summation also. This is how exactly your electric field due to system of charges goes. This was just done to make you understand how exactly it is connected if there are n number of charges, or how exactly to give only for one charge, how will you give the electric field. This is based on Coulomb's law. This formula is based on Coulomb's law. Okay. Next is physical significance of this electric field. You have it, that is electric field. It is a characteristic of a system and it is independent of the test charge. Field never depends upon the test charge. It depends on the source charge. Okay. Next, the force experienced by a charge Q through an electric field can be given as F is equal to Q into V. This equation is derived from electric field, is defined as force per unit charge. So your Q goes with electric field. So you have vector F is equal to vector E into Q. So this holds good for force. Okay. So that's all about your physical significance of your electric field. Now, in order to show the presence of electric field, we have to have a pictorial representation to show that the field is moving from this place to this place, which is an imaginary concept. So now, for that we have something called as electric field lines. So here we make use of lines to represent the electric field. The pictorial representation of electric field charges gives you the electric field lines. How is it? So we have a source charge over here. Consider you have a source charge over here and a test charge over here. Okay. So suppose if that's the case, how exactly it moves? The movement of from positive charge to a negative charge, how exactly the field lines move? From positive charge, the field lines are directed away. Towards the negative charge, the field lines is towards. Okay, directed away from the charge towards the negative charge. Okay, so you can see with the help of this arrow mark. And in physics, why arrow mark is very important? In order to represent the direction of motion, towards which direction it's moving. So, path in an electric field line, it can be straight or curved path, and the tangent drawn to it, these are the tangents which is drawn to it. Okay, these tangents to it at any point gives you the direction of the electric field at that point. This is known as your electric field lines. Understood? So next we are going to electric field lines are stronger near the charge, but as it is moving away from the charge, it becomes weaker. Okay, so electric field is weak when it is away from the charge. Okay, so those two are one of the concepts what you have to remember. Next is field lines around a single positive charge which are directed radially outwards. So we have a single positive charge over here. Consider we even have a single positive charge here radially outwards. So the outward direction turns out to be in this manner. It's not attracting each other because both also are moving away from the charge. Field lines around a negative charge are radially inwards. So we have two negative charges to which we have radially inward concept. So if we consider in the same way as that of a positive charge, this is inwards. Only the arrow mark gives you the correct answer, whether it is correct or whether it is wrong. It gives you the answer. Clear? The field lines around a negative charge and a positive charge it is also called as dipole because it has two poles, positive and negative charges. So this is positive, this is negative. So we just draw the lines. In a bigger version, we have this connection. Draw the lines. In a surrounding version, we have this connection, which is the connectivity of these charges. So, away from positive charge, away from positive charge, away from positive charge, towards negative charge. Okay. Always the field lines move away from positive charge towards negative charge. This is how we give the field lines in case of dipole. Next, properties, which is one of the most important question in exams, properties of electric field lines. Field lines which starts from positive and it ends on negative, as you have seen in a previous slide. Field lines, it is continuous curve without any breaks. So here you can see breaks, but it is a continuity of it. It continues up above, it continues below. We just don't draw everything continuity, we just leave a free space over here which shows the continuity. Tangent drawn to a electric field lines represents the direction of electric field as studied. Two lines never cross each other, it just move from one place to another place without even intersecting each other. Electric field lines do not form any sort of closed loop over there, and electric field lines are always normal to the surface of the conductor. So suppose if this is your surface of the conductor, normal in the sense it should be in 90 degree. Okay, theta should be in 90 degrees. So electric field lines is always normal to the surface of the conductor. It is always 90 degrees to the surface of the conductor. So these are some of the properties of electric field lines, and we have, this is the representation of electric field lines away from the positive charge towards the negative charge. Okay, so next is electric flux. It is a strength of an electric field at a point when a number of field lines crosses over the unit area. So suppose if this is a conductor and we consider only this part of the conductor and their electric field lines are passing through it at 90 degrees. So what is electric flux? It is the strength of the field lines. How do you calculate the strength of the field lines? We just consider a certain part of the area of a conductor and measure how much amount of field lines are passing through that particular area, which gives you electric flux. Next, we are going on to how to calculate it, how to get the equation of it. If S is a surface which is divided into large number of surface elements, suppose if this is a surface which is divided into large number of surface elements like this, out of which one is S dash and this is S. Okay, let theta be the angle between the direction of the electric field and the normal E cos theta. Okay, so normal electric field is normal. If it makes an angle, it becomes E cos theta is the component of intensity which is along the normal. Yes, it's called as E cos theta. Then the electric flux through that surface element ds, S dash or ds we can call, then the flux through that surface only from this surface turns out to be d phi. Electric flux is given in terms of phi. So change in flux is equal to E cos theta into ds. Okay, this is about your electric flux equation. D phi is equal to E cos theta into ds. Next is dipole. Pair of equal and opposite charges which is separated by a small distance. Dipole. Positive pole and a negative pole. It is a pair now. Pair of, it is equal charges plus q and minus q, equal and opposite charges which is separated by certain small distance, be it as r, or even you can call it as 2 times that of a, and it is separated by a distance 2a. This is nothing but electric dipole. Pair of equal and opposite charges which is separated by a certain distance, that is 2 times that of a. Electric dipole moment. How do you give a electric dipole moment? Moment is given in terms of vector p. So how do you actually give this? Electric dipole is a vector quantity. Moment is a vector quantity and the magnitude is equal to the product of magnitude of either charges. Magnitude means value of either of the charges. So electric dipole means we have it as plus q minus q separated by 2a. Product of magnitude, that is pre-vector, is equal to product of magnitude of either of the charges, that is q, and the distance between them is 2a, q into 2a. In order to balance this vector quantity, we have p cap, that is a unit vector. So vector p is equal to 2aq and p cap. This holds good for your electric dipole moment. Next is the field of an electric dipole moment. The electric field E, that is a vector E, at any general point P, it is obtained by adding 2 electric fields, that is E1 and E2, due to positive charge, negative charge, or we can even call it as a dipole in a parallelogram law of vector addition. Okay, so how exactly we go with it? We need to check the result what happens when a point P is on the dipole axis as well as equatorial line. So now today let us derive on the dipole axis. So how does it go? Electric field at a point on a dipole axis. So we just draw a dipole over here. Positive charge is at certain distance from a negative charge. So this is plus q, this is minus q at a distance 2a. The distance from here to here we call it as 2a. The influence of this dipole is over a certain point P over here. So the electric fields which are given over here can be called as E1 and E2, represented as E1, E2. Let us just divide this dipole into half and we call it as O. Let a distance be drawn from a point P to point O. Let P be a point at a distance R from this midpoint O. Okay, so we have this as A and this as A because together it makes 2A. And we have a point R which is correctly at distance from distance O to P. The arrow mark should stay there itself. It shouldn't extend. Okay, so we have this dipole moment. Okay, so electric field at a point on the dipole axis. Dipole is this. In the same axis, what exactly is the influence of the electric field over P? So we have electric field E is given as, E1 is given as 1 by 4 pi epsilon naught Q, and E1 is due to the charge plus Q. So Q divided by, from here to here, it makes R. But if it has to stay at Q, we are checking the value of or the influence of Q on P. So we have to minus A, because from Q to midpoint it is A, R minus A. So it is R minus A the whole square. Consider this as equation 1. Okay. Next, we have electric field due to E2. So here also we have 1 by 4 pi epsilon naught Q divided by R plus A the whole square. This is called as equation 2. Because influence on that electric field influence, second electric field is due to minus Q. Minus Q, from here to here it is R, and extra it is A. R plus A. You have R plus A here. Yes. So this is due to Q1 and this is due to Q2. There are two charges. Now, since it is a vector quantities, vector has to be balanced. So I give it as P cap and it is minus P cap. Why minus? Because it is negative of Q. No, I took it along the P cap itself. Yes. So you have E1 as well as E2. Of course I have. Now, we have to check the angle of it. Now, we have to sum up, because it's the influence happening at point P due to plus Q and due to minus Q both also. So E1 also is there, E2 also is there at the same point, that is P. So we need to calculate E. Total E calculation is given by E1 plus E2. So let us calculate E1 and E2. Vector E is equal to 1 by 4 pi epsilon naught Q divided by R minus A whole square into P cap minus 1 by 4 pi epsilon naught Q divided by R plus A whole square into P cap. P cap along with minus we had seen in a previous formula, that is equation 2. But now I have multiplied that plus, that is center plus, with the minus. So plus into minus, I have got minus. Next is vector E is equal to, which is common out, take it outside. 1 by 4 pi epsilon naught along with Q into 1 by R minus A the whole square minus 1 by R plus A the whole square, and we have P cap. Next is vector E is equal to Q by 4 pi epsilon naught. LCM of it gives you A square, A minus B whole square, A plus B the whole square. This is of the form R square minus A square the whole square. So it becomes R plus A the whole square minus R minus A the whole square into P cap. Vector E is equal to Q by 4 pi epsilon naught. Solve this. A square plus B square plus 2AB. So 2RA minus of A square plus B square minus 2AB divided by R square, A square whole square and P cap, which is equal to Q by 4 pi epsilon naught. R square cancels, A square cancels. So minus into minus, it's plus. So 2 into RA, you get 4RA divided by R square minus A square the whole square into P cap. So from this we can take 2A with Q with P cap. So from here Q goes, from here A goes, from here 1, 2 goes and 1 will remain. and from here P cap will go. So total is vector E is equal to 1 by 4 pi epsilon naught lies there, and you have 2 times that of R into P vector divided by R square minus A square. So this is the final equation of electric field at a point on a dipole axis. Suppose if you consider R is very much greater than that of A, we can neglect A. If you neglect A, you get an equation vector E is equal to 1 by 4 pi epsilon naught 2 times that of R and P vector divided by R square of the whole square. This square is over here. So it becomes R square plus square becomes R4. So which is equal to 1 by 4 pi epsilon naught. R cancels with 1 R. So 2 divided by R cube of P vector. This is the complete set of equation for electric field at a point on a dipole axis. If suppose this is the actual electric field at a point on a dipole axis, this case will arise only if R is greater than that of A condition. Okay. So in today's class, we have studied about electric field lines, electric field, dipole, dipole moment, as well as having all these things, we have studied electric field at a point on a dipole axis. So let us all meet in our next upcoming session. Until then, have a good day. Thank you.